Hi, my name is Jerry Chow. I'm an IBM Fellow and the Director of Quantum Systems at IBM Quantum. I'm holding right here Heron, our most performant quantum chip. And I'm going to take you into our quantum characterization lab to show you how we test it before it goes into our deployed systems in our quantum data center. Follow me. Now here's our quantum characterization lab. It's actually really secure, so not only do you need a badge, but you also need a Retina scan, and most IBMers don't actually have access to this.
Please enter your eyes in the mirror.
All right, so now we're in our quantum characterization lab, and this is where we do a lot of the characterization, testing, and qualification of our Heron devices. Heron is one of our utility scale quantum processors, but it's also our most performant ones. At 133 or 156 qubits with our latest generation, we've been able to push the limits in terms of its quality and what we can actually run accurately with quantum circuits. Most recently, we've demonstrated that we can actually push this all the way out to running 5,000 gates using error mitigation. Now, right here is actually where we do a lot of the preparation of the devices, getting them ready and to be packaged up and put into our characterization fridges, which are right in this lab. Now, if you look over here, this is actually what Falcon looks like from a few years ago. So Falcon was 27 qubits. You can see sort of the package size that it took in terms of the board, printed circuit board, to actually hold the device, and this would go to the bottom of our dilution refrigerator to be cooled down. And contrast that with Heron, right? So Heron, this is our first generation Heron, 133 qubits. You can see the size of the printed circuit board to address this particular device, certainly much larger, but with more complexity, and the added benefit, of course, now with the tunable coupler architecture to push the limits of our underlying 2-qubit gate qualities. So really an evolution of the technology and sort of the scaling of what we have to test and characterize right in this lab. And now I'd also like to show you the evolution, much like Falcon to Heron, of the internal wiring that we've achieved also to really scale up the testing capability and volume of testing that we can have in this lab. So right over here, what you can see is with these trees of wires, you can see many parallel coaxial cable lines. These coaxial cables carry the microwave signals that allow us to address the qubits or read out the qubits. And what you'll notice with them is that they take up a lot of space. In some cases, they're lower density. In this case, they're much higher density. In terms of the amount of footprint, one can see just how much space it can actually take and really be a limiting factor in terms of the number of signals that we can actually have in a real quantum system. But we've evolved to this kind of flexible signal delivery technology. And what you can see is that now, basically these are about the thickness of a piece of cardboard, and yet they allow us to drive many parallel signals all in one card. We connect them together at various points, mount them into the dilution refrigerator in the same way, but at a much higher density that's possible, as well as at a much lower cost. So this is also this evolution of the underlying system technology that allows us to scale up our capabilities of testing. Now let's go over to the actual fridge where my colleague Daniela will show you how this all comes together. Hey Daniela.
Hi Jerry, how are you?
Doing well, how are you doing?
Excellent.
So I think I just talked a little bit about Heron and the latest generations of wiring, and maybe you could just show us how it all comes together here.
Sure. So here we have our typical dilution refrigerator that we use for testing large devices. Our latest processor, the Heron, it's hiding in this rectangular box, which is a magnetic shield against radiation and magnetic fields.
So the board that I showed before kind of just
it's kind of
underneath
sitting
there, right?
around here.
Yeah.
And we have the typical components of a dilution refrigerator. So we have the flanges that go at different temperatures. So everything that is below this flange is at 50 millikelvin. Here we have 100 millikelvin, 1 Kelvin, 3.5, and so on. And since we are a research, dilution unit, we are doing a comparison between old and new, because we used to use this coax high density wiring, and now we are using our in-house developed flex technology, which is a lot more compact. We also have our amplifier 2-pack can, they are quantum limited amplifiers, which we develop here, and they are helping improving our readouts. And we are pretty much ready to close it up.
Great, so let's take a look at how we can actually close this up.
So our payload is loaded, the fringe is pumping out. In about 2.5 days, I'll be able to start running measurements. Heron is a little bit more special than our previous devices. Our 2-qubit gates are optimized using couplers. They need to be tuned and optimized themselves. So in a testing lab, you want to measure each individual qubit, each individual coupler, each individual 2-qubit gate in order to determine performance. We have an example where we are looking at the previous device measured. What do we typically measure is full qubit performance on all the 156 qubits, and that means from readout frequency, qubit coherence, and also flux coupler tuning in order to optimize the 2-qubit gates performance. Once we know all these elements about the payload, we decide if we want to have it deployed for the client systems. We have a data center which is in Poughkeepsie. There our quantum systems can be accessed from all over the world by our clients and partners. And now back to Jerry.
So that concludes our lab tour of our quantum characterization lab, where we look at our latest and greatest herons. If you want to learn more about our quantum processors, please subscribe to our channel.